Okay. I put a file here called Lecture Notes, Chapter 4, and that is a print of all my slides I'm going to be going through. So in the future, if you see that and you want to print that off and then take notes directly on the slide, that's what I'm thinking of. I can show you what it looks like. So there's let's see, what, 3 slides per page, and then an area over here so you can take notes. Now these slides are from the book, and the slides tend to be, in my opinion, busy. I actually tried to simplify them, but that almost was like starting from scratch, and there were 60 slides, and I just didn't have enough time. Oops. Okay, at the beginning of each chapter, I talk about what you need to get out of that chapter. Okay? These 10 learning objectives basically fit. This is what basically the test on learning objectives. There are the problems I gave you earlier, work through all these. Now these are probably the bottom half, probably the bottom half is very straightforward. The top half is more historical. How we ended up with the atomic model we have now. We'll see how that unfolds here in a minute. Okay. So there are some basic tenets about our physical world. One is matter. That's anything. It's composed of atoms. Okay. The smallest identifiable atom is called an element. There are 92 naturally occurring ones, and that number varies depending on, some people think there's 90, other people 91, 92. Element 92 is uranium, and most of the time people think that up to uranium is naturally occurring. After that is man or female made. And it goes up to 118. And they're named all the way to 118. I call them natural elements, synthetic elements. Synthetic ones are, some of those are really, really dangerous. Does anyone know why the synthetic ones might be dangerous? Yeah.
Because it can go through a chemical reaction and break down into different elements.
Yeah. Who's heard of Levin? No. Levin. He's a Russian spy. He was killed by the KGB at the time for being a double agent with the United Kingdom, and he was killed with something called polonium. Polonium is a naturally occurring element, but it's also very radioactive. What they did is they spiked his food. It was a 007 kind of deal. Big giant elite meal. And you can treat him to this thing, and they spiked his food with this alpha radiation emitting chemical, polonium. And he was so radioactive, they had to put him in 2 tests. He died 6 months later of pancreatic cancer. No one liked double agents, by the way. But a lot of the synthetic elements are radioactive, like plutonium. And the problem with plutonium, it lasts forever. And plutonium is made a lot in nuclear reactors. The kind designed to make plutonium, like Hanford up in Washington State. We have a horrendous problem now with the safeguarding of that stuff. It's great for making a dirty bomb. Who's heard of a dirty bomb? Anyone? Okay, what's a dirty bomb? It's nuclear based, right? What else?
You know, like it takes forever to like its half-life is like super long.
Depends on what they use in the bomb. Sometimes the stuff is short, sometimes it's long. Most of the time it's long. So it's radioactive. Does it require any kind of technical expertise to make it? No, that's the problem. If you are anyone on the street, I could grab the next person walking by out here and they can make a dirty bomb. What you do is you take radioactive material and you grind it up into a dust, and you go, that's a dirty bomb. Basically, you're just spreading fine particles of radioactive substance around. You can have a crop duster, ventilation system, anyway, anything like that. And it's extremely easy to make because it doesn't require anything. Guess what nuclear reactors produce besides power? That's right. The fuel, the spent fuel, is very radioactive. And you know how they guard the nuclear power plants? Usually they don't. And they have it all on site. So anyway, there's a lot of interesting stuff going on with the synthetic elements. Not a lot of it good. Okay. Here's uranium right here. Right here. So everything beyond that is synthetic. Okay, now I want to talk about the historical development of the atomic model. It starts a long time ago. There's a Greek guy named Democritus, and there's another guy named Aristotle. And they were like counterpoint to one another. Democritus said that you can take something and divide it, 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 and all of a sudden it stops retaining its intrinsic characteristics. It's like we took an apple, cut it in half. Do we still have apple? Cut, brand new Jinsu knives, cut it up, all of a sudden you reach the point where it stops being an apple. That's what Democritus was talking about. Atomos in Greek means no cut. And that's where the word atom came from. Now, the interesting thing is Aristotle believed that everything came from, earth, wind, and fire kind of stuff. And because he was much more powerful than Democritus, his ideas lasted all. So anyway, these guys, the first ones to actually postulate the existence of an atom. Now, alchemy was widespread in particularly Europe towards the probably from 1600 back. And their main goal was this: they want to convert cheap metal into gold, lead into gold. That was their idea. That's how they earned their quote-unquote king's deal. There were things like elixir of life they were looking for. What made something less alive? Concept of ether went along with that. And there were some really interesting things they did. The problem is, if you think about Europe at that time, there are these isolated villages. One's called London, one's called Paris. At the time, though, they were really tiny. And how do you communicate between villages in the 1600s? Huh? Yeah, walking, horseback, donkey, really, really slow. So that the communication between these large villages was very poor. Additionally, they didn't speak the same language. So that's one issue with science, is you have to standardize what you're talking about. So if I do a lab, and I propose I discovered a new element, someone else has to recreate it. That's called peer review. If the peers cannot duplicate it, it's not accepted. And these guys, they didn't have anyone to review. Also, the language is very unclear. Water in, these are Spanish people here. Who speaks Spanish? Okay. ¿Cómo se dice water en español? Right. Okay. In English, it's called water, not the same word. The chemical is the same. Is there anyone here from the Middle East? Speak Arabic or Russian? Huh? What's water in Russian? Is it, did you say water? Oh. So, but it's the same stuff. We know it's the same stuff because the formula is the same. In these days, they didn't know about formulas. So, aqua, water, the Russian version, not the same thing. So there was a lack of standardization. And these two deals is what killed alchemy. So as they started to progress, they started to minimize these challenges. Now, Western Europe was way behind two main centers of science. One is in the Middle East, one is in China. Europe was way behind these things. This guy is considered the grandfather of modern chemistry. And we're talking about the 9th century. That is a long, long time ago. Have you ever heard of this guy? No, probably not. No one gives any credit to anything outside of Europe. The Chinese, they did a whole bunch of stuff. They were involved with metallurgy, medicine, gunpowder, pottery, ceramics, dyeing techniques, way ahead of Europe. And these two centers of scientific knowledge is usually ignored. Like, for example, our numbers are Arabic. A lot of people don't realize that either. Okay, the first European guy to kind of put together a solid theory was Dalton. He believed in the idea of Democritus, didn't believe in Aristotle's perspective of matter. These are his tenets. Now, there's some issues with this, but basically, don't know this is like long time ago. Okay, so each element has tiny particles, indestructible particles down before the identity of the particle is not that identity anymore. All atoms, this is kind of a weird one. All atoms that distinguish themselves between one another are the same. In other words, if I have a hydrogen atom It's the same as another hydrogen atom. They're different. And you go like, well, duh, of course. Right? Anyway, and atoms combine in simple whole number ratios. Like, what's the formula for water? H2O. It's not H 1.9 0.9. It's H2O. Integers. And basically, he's saying you can't have half of an atom combining, or a third of an atom. Okay, a little while later, there's a guy named Thomson. He came up with an electron covered this negatively charged particle within the atom. He called it a corpuscle. And my other stuff. Then they changed the name to electron. He also came up with a concept of something needs to balance that negatively charged electron. So he says something positive has to exist to counteract all these negatively charged electrons. So he sort of discovered protons at the same time. It's kind of a backdoor logic. He also said there is no organization inside the atom. Basically, it's like a goofy ball with random electrons in it. And those other mysterious positive particles as well. And he called it the plum pudding model, similar to plum pudding in those days. Basically, you got pudding randomly scattered fruit or whatever, or like tapioca pudding. Okay, plum pudding model. It was the first model, now again, European. The first model of kind of what's underneath inside of that. The three things. First model called plum pudding model found electrons and proposed protons. Those three things are what Thomson, no P, it's Thomson. Remember now, everyone, I have these slides for you already. Okay. Now, one thing scientists have to do is they have to confirm what another scientist has done so that they can credit it. So Rutherford wanted to confirm the plum pudding model. Remember, the plum pudding model now has negatively charged electrons inside. So what Rutherford wanted to do was, well, if I shot an atomic bullet through that, it should go right under. Or one or the other. Okay, so think about, we're going to go to Walmart now and buy a really cheap BB gun. And we're going to secure the BB. Think of that. This is a Walmart gun. Comes to be shooting alpha particles. Right into something called gold foil. Gold foil is very, very thin. And what happened was Thomson's model could not be duplicated. What happened is that most everything went through. Occasionally, 1% of the time, when we bounce back. Only consistent with Thompson. So Rutherford's going, wow. I can't keep up with Thompson model. So what Rutherford proposed was that most of the mass inside of an atom is in a little tiny area. What do you think that little tiny area inside the atom is called? Huh? Nucleus, right. Now, the wild thing is, okay, so this is the nucleus. That's from. But what about the other part? This is the wild part. It's really wild part of it. And you have a lot of trouble convincing people that this made sense. What is out here? Now, look, all the mass of the atom, 99.999% is right here, that little dot. Let me give you an idea of how little that dot is. Let's go to a large football stadium. We take a marble and put it in the middle of it. That's the size of the atom, the whole stadium. Where 99.99% of the mass is in that little marble. So it's dramatic. Truly dramatic. Nothing. So what I'm saying is when I go like this, see, that's what Rutherford was trying to do. So it weighs 2 pounds, these little dots of mass. And the other thing wild about the dots of mass is there are protons in there which are positively charged, and positively charged particles don't attract, they do what? Opposites repel. Unlike relationship. So you've got a force in there called a binding energy that keeps those protons that are extremely close together from flying apart. That's where we get the nuclear energy from when we split the atom. So this model was that we had electrons in there. Another interesting thing is why don't the electrons, why aren't they attracted to the positive nucleus? Yeah. They're apart. That doesn't make any sense. Rutherford was grappling with all these ideas. But that's the Rutherford model. Rutherford invented the concept of the nucleus. Big deal. And again, electrons, according to Rutherford, have no organization. They are random. Now, there's not a slide on the next guy I'm going to talk about. Now, the next guy came along and said, that's BS. Electrons have got to be organized. All this happened around early part of the last century. Einstein was around, Planck was around, Rutherford was around, or took Rutherford's model and said the electrons are organized, not randomly distributed. He proposed. Who has seen Men in Black? Okay, what was on Orion's belt? Huh?
Yeah,
It was a long time ago, wasn't it?
On the tap?
It's hard. Huh?
Is it like a marble or something?
Yeah,
A
what-
galaxy?
Right. Galaxy inside a little pendant hanging on Orion Pax collar. And what does the galaxy look like? Exactly. A planetary model. So Bohr which is an elegant map that electrons are organized into orbitals. And orbitals are finite. The electrons can only reside on the orbital, no other place. The idea was that they revolve around, just like a little solar, just like Men in Black. Okay, and then from there, we have the quantum model, which is yet another elaboration on Bohr's model. Quantum model says that there are no distinct orbitals. There are places where electrons can be, and they're not planetary. So statistically, this is the way it works. If you were to go down to railings and walk around the side of railings, there's probably a spot where there's a whole bunch of cigarette butts around. Smoke, you can't smoke inside railings. You're an employee, where do you go? You have to go outside. And so there's a good chance if you go to this one spot, you're going to find some cigarette butts, right? You don't know how they got there. You don't know if it's employees or customers, but you know where to find the cigarette butts. That's quantum model. We know where to find electrons. We don't know how they got there. So statistically, certain areas around the nucleus has a higher percentage of electron sightings than other parts. That is the modern model. So it's not very concrete. But there's tons and tons of research. Okay, so that's kind of the idea of Greeks, the modern idea of the atomic model. Okay? All right, let's move on here. Now, if you look at these numbers here, now electrons have a charge of -1. Protons have exactly the same amount of charge, only positive. Exactly the same amount. This is like infinite big things. Exactly the same amount. There's another particle in there called neutron, and neutrons have no charge. But the mass of a neutron and proton are approximately the same. And you see how small these guys are? 10 to the -27. Pretty small. Look at the mass of an electron relative to these guys. That electron is significantly smaller. It's by like 10,000 times smaller. Yet its charge is a lot. So it's a high performance little particle. Small mass, big charge. Big mass, big charge. Okay. We already mentioned this, opposites attract. It's like North and South pole and a magnet attract one another. Like charges repel. You can neutralize one charge with the opposite charge. Like you have a proton, and an electron produces a net charge of 0. I want you to think, what particle are we talking about that has 0 charge?
A stable one?
Yeah. Very stable. What particle has no charge? Huh? Neutron. Going back to that previous slide, remember there were 3 particles. We had proton, neutron, electron. Protons have a positive charge, electrons have a negative charge, neutrons have 0 charge. So a neutron is made up of a proton and an electron. So conceptually, we have electrons around the nucleus. We also have electrons inside the nucleus, buried inside of a neutron. So a lot of people have never heard of that before. And electrons can be inside a nucleus. Okay, let's see here. Now, when we talk about 118 elements, what makes nitrogen different than oxygen? It's the number of protons, period, no exception. The number of protons determines the element. When we get into nuclear chemistry, we use something called transmutation. We change one element into another. How do you think we do that? Yeah. The proton number changes. The proton number changes, the element changes. Electrons can come and go. Neutrons can come and go. But if protons change, the element is not the same. Nuclear fusion, we take uranium, special isotope uranium, and we blow it away with a neutron. We bombard it with a neutron. It bursts open because it's not stable anymore. Into krypton, bury it. Protons, there are protons that change. That's why it's no longer uranium. 2 new elements. Now, on the periodic table, every single periodic table. This is a really basic one. Basically, every single periodic table has to have the symbol and the number of protons. And also, what we call an atomic mass. Okay, sometimes the name is included, sometimes it isn't. Some professors like you to memorize the periodic table. I don't believe that, but some people do. Like we had departmental meeting about how much of the periodic table should our students memorize. And everyone here, does anyone here not have a smartphone? That's so cool. Well, I memorize something, rip out your smartphone within seconds. You have that information. Not everyone needs that. Okay, so minimum part. So we have a chemical symbol. The symbol is either 1 character or 2 characters. If it's 2 characters, the first one has to be uppercase, no exceptions. The second part has to be lowercase, no exceptions. We have something. CO and CO. What's the difference between this and that? Alpha and what? Yeah, it's carbon and oxygen, right? What about the bottom? 1 element, because it's got a uppercase or lowercase. This is carbon monoxide, that's cobalt. CO. That's why it's very important when you write the symbol, it has two characters, make sure. No exception that the second one is lowercase. Some people like to print in all uppercase. When they print in lowercase, they make a smaller version of the uppercase. I had a Coast Guard officer that was a inspector on container ships. And he was required by international law to do that. I said, sorry, make sure flash things lowercase. There's no warmest one. Here we are talking about budgets. Here we have a nice. Okay. All right. Early on, there were some more chemists and physicists that were like Bohr. Bohr said, you know, those electrons have to be organized. And there were two, one was a geologist, one was a physicist. And the geologist came up with this idea first, that he didn't publish. And the Russian, Mendeleev, came up with the idea as well, but published. So guess what everyone credits the first periodic table to? The one that published, which is Mendeleev. He noticed that certain elements have chemical properties that are similar. So what he came up with first thing he did was put all the elements by mass that were known at the time. But he noticed that certain elements had similar chemical characteristics. So what he did, instead of a one-dimensional listing of all the elements at the time, he chopped it off where the similarities existed. So cut it there and took this piece and brought it there. Took this piece, brought it there. We ended up with a two-dimensional version of his listing of all the elements. That's how this chart came to be. Instead of one big long one like a long train, we chopped it up into pieces by chemical similarities. And that's why they call this concept of grouping the elements, because the chemical characteristics and properties are almost the same. So there are columns and rows in the periodic table. The columns are where the chemistry is similar. So everything in a column is going to have similar chemistry. So that means, for example, this guy here, calcium and strontium, are going to have similar chemistry. Carbon, silicon. Sodium and potassium. Okay, let me show you how this applies. Go to the doctor. The doctor says your blood pressure is too high for a person. I'm all and all people. No, that's not the good reason. So, I cook myself, and I like, and you have to put that on food. Flavor. And what is that called? Salt. Salt. Okay, sodium is along for the ride of the chlorine. This is what makes this molecule salty, chloride ion. This has no taste. So this is the culprit for my high blood pressure. So what would you guys prescribe for me? Fix my problem. Low sodium diet. There's a number of ways to do that. I'm at Rayleigh's in the spice department. I look down towards the bottom where all the salt is. What's also that? That contributes to the salt. You guys heard of light salt? If you haven't heard of it, and you have high blood pressure, this is frequently what a doctor will prescribe or a nutrition. Light salt. Well, what is light salt? Well, if we want to maintain the salt taste, otherwise, what's the point? We got to get rid of the sodium. So let's use our chemistry now. Let's go over here to sodium. And remember in the column here, the chemistry is the same. So what element in here is close to sodium? There are two. So here's sodium. What's this guy here? Well, potassium. What about above it? Lithium. So light salt is potassium chloride. So it acts just like sodium chloride in your body, except no sodium. But it's still salt. And it's only because periodic table columns thing. This is another example. Right up here. One problem with a nuclear bomb is it produces a lot of strontium, radioactive strontium. That's SR, which is right here. What's it near? Chemical. What's it above? Calcium. Okay. Calcium. What do you know about calcium in your body? Bone. Low calcium, you have issues with weak bones. So your body taking calcium needs it for strong bones. Guess what it also takes in if it's around? Strontium. If you're around a nuclear bomb like Chernobyl, basically was a nuclear bomb, you absorb strontium instead of calcium. And it happens to be radioactive. So what is made inside your bones? Huh? Bone marrow. What does bone marrow make? Blood. Red blood cells. If you inhale strontium, you end up with leukemia. So leukemia is a very common radiation sickness. The reason is because of the strontium, it's in your system, affects your bone marrow from producing red blood cells. And it's because of the chemistry is the same. Yeah.
Isn't strontium levels also used to measure like a general estimate on how old a skeleton is, like how old the person is?
Usually that's carbon.
No, I mean like because of the nuclear tests in the United States, they blew winds with radioactive material across the north, and I know that they use it to like date in like wine because of radioactive elements in wine, but I think they also do it for.
Well, they can use a lot of elements to do things. Oh, something. It has to do with the half-life of the. Let me talk about the.
Oh,
Yeah, that's what we're talking about here. Every curve on that exponential curve is different on every element. So you know the life cycle of that. But if you know the level, you can predict through how many half-lives or portions of half-lives that existed before. I haven't heard about strontium. Why don't you look that up? Did you send me an email remind me that?
sure. Let me bring it up.
Okay. Now, when this radioactive fallout from Chernobyl started spreading all over Western Europe, it ended up in fields where they're grazing cows. Grazing cows eat grass that was radioactive strontium on, gets into the milk. And what's a good source of calcium? Milk. So because strontium and calcium are similar chemically, it's embedded into the milk. You drink the milk. That's another way, a route by which radioactivity gets into our body. There's a lot of examples of this. Carbon. Our body, the structural part of our body is carbon-based. They use a lot of silicone on body parts because it chemically is right underneath carbon. Now you're gonna have to know 4 groups. These first 2 and the last 2. Okay, so alkali metals is the first one here. We're going to call that group 1. What's up there? It says 1A. Okay, you need to know group 1, alkali metals. The one next to it, called alkali earth metals. And they're very similar, but not the same. Then we're going to jump over here to the second from the last one. That's group 7, and that's called halogens. And the last one, group 8, is called inert gases. What does the word inert mean?
It's like also using law of inertia to like not have the tendency to move or change position.
What do you think it means chemical? That's I totally. What do you think it means chemical?
It doesn't like to have a reaction.
Exactly. In other words, why do we have lead ring? Like gold ring. Why does gold ring better than lead ring?
I don't know if it's kind of like poison. or something.
Yeah, because it reacts with your skin. The gold ring doesn't. Well, gold is more inert than lead. Inert gases are the only stable element in the reaction. So you can go and find helium. Helium's in a short supply, by the way. Neon, argon, krypton. Those are in our gas by themselves. So they are monoatomic. Everything else in the periodic table is not particularly stable. So what happens is it binds up with something else to become more stable. Well, there's a theme in this class I'm going to talk about a lot. That unstable things become more stable, not the other way around. It's like when I drop this, it goes down, it doesn't go up. Down is more stable. Chemically, the same thing. When you put water in a glass, does anything happen to the glass? Dissolve? No, it's glass, right? That means that glass is very, very stable. Otherwise, it will combine with the water for something else. Okay, so these four groups are chemical families you need to know. There are 7 periods. Periods are rows. So these are periods. So there's first period, second period, and there's no tendency going horizontally like there is vertical. Okay, so there's rows, periods, columns, groups. Groups are aligned for their chemical similarities. Now, you're going to find these names are kind of wild, and they're historical. You know, like lead is PD, isonate LD. Gold, thorium, silver, argentum, iron and stuff. These are all either Latin or Greek bases. They're also named after countries. Polonium is after Poland, francium is after France. These are synthetic ones. They're synthetic, let me give you a hint on some. Whenever the atomic mass is in parentheses, that means it's synthetic. These are all synthetic. They're made in a reactor or a cyclotron. And some of them are very, very stable. And other ones are horribly unstable. But we make them anyway. Sometimes the elements are named after their physicists who discovered them. Like there's Einsteinium, curium, and here is Mendeleev, and here is his one-dimensional row. We started seeing similarities, and then once the similarity identified, we chopped them and stacked them on top of one another. Now, alkali metals is group 1. They form a +1 ion. I'm going to talk about ions in a minute here. So everything there is +1. The alkali earth metals, +2 charge. The halogens, -1. The inert gases are 0. Group 6 is a -2, -3, +3. And we're going to learn why those numbers exist. So for right now, just need to know that group 1, +1, group 2, +2. There's 8 columns across. Group 7, -1, group 8, 0. And again, the inert gases are the only elements that are stable enough to be by themselves. Everything else is not stable. It has to combine itself. And you get these rare metals that occasionally will be by themselves, like gold and silver. But it's not common. Most of the time, elements are tied up with oxygen. Oxygen is very prevalent in the atmosphere. Most things are oxides, because that's more stable than the bare element. Okay. There are 3 main groups of elements. The biggest group is called metals. And what's the opposite of metal? a nonmetal. And in between the metals and nonmetals are metalloids. Now the metalloids are kind of cool. In 1947, in the United States, Bell Labs, using a metalloid, discovered something, or invented, I should say invented something. Does anyone know what that is? This is real nerdy. 99% of the stuff you do every single day involves this invention. No. What's inside your phone? Huh? Yeah, what else? Yeah, keep going. Okay, there's the batteries, there's the speaker. Huh?
Transistor.
Transistors, exactly. Only they're really, really tiny now. Back in 1947, they were quite large. So Bell Labs invented the transistor. Okay, and again, it's using germanium metalloid. What they did, a metalloid, if you apply a voltage to it, will change its chemical characteristics. Okay, so let's go to the definition of a metal. Okay, metal. Tell me something about a metal. What is the chemical characteristic of a metal? Shiny. Good. So what do you think a non-metal is? Dull or not shiny? Okay. What are the characteristics of metals? Yeah. Okay. And then the opposite would be like fragile, right? Okay. What else? Metals. What is wire made out of? Copper, and that's a metal, right? So what else? Yeah. Say what? That's true. No, no, that's exactly right. You do. Yeah, if you have a pan made out of metal, you're holding it over the fire, it's hot. If you have a piece of a non-metal over fire, it doesn't get hot. And it doesn't conduct heat. So, what other thing? What else? You guys are doing great. Especially first.
That's like non-reactive on its own. It's like something else.
Well-
I feel geocast, we like literally brought dilute acid into the field, just like poured it on the ore and stuff to see what.
Yes, that's one way of determining the metal,
Yeah.
putting concentrated electric acid. Exactly. Yes, but that's not, yes, I totally agree with that, except it's not real clear cut. But these are really this or that, not a lot in between. Yeah, I agree with you. If I have a piece of wire and go like this, would it break?
What's it?
Bend, doesn't it? So metals are ductile. So you can squeeze them, bend it, all that stuff. Okay, now the one thing. So a metalloid is in between a metal and a non-metal. So that means the metalloid's characteristics are in between these. And this is the one transistor. And so what happens is okay, Bell Labs took some germanium, pieces of metal, attached a wire to them, and when you put a plus charge on the wire, the germanium conducts electricity. When you put a negative charge on, it is a non-conductor. So it's one way or the other. One way. Instead of writing out the word conductor, let's put a 1 by it. And when it's a non-conductor, put a 0 by it. So we have a 1, 0, 1, 1. What does that look like? Binary. The metalloids allowed the world to work in digital format. The metalloids are either like metal or non-metal. What they invented early on was something called a diode. Di meaning two. So metalloids are really, really important. They're also important for metallurgy. And we have a real problem in this world because the more exotic metals we need are in short supply. Certain countries of the world hoard them. China being one, Russia being one. They have mines of these rare earth metals that are extremely important in things like gas turbines, very, very hot. You need rare earth metals to mix with the iron and chromium and stuff to make them very, very strong. So there's a big disparity in that, and they're using their leverage. Okay, so let's go on. So anyway, metals, non-metals, metalloids. And we talked about some of the properties of metals, properties of nonmetals, metalloids. Okay, so that's one way of grouping the periodic table. Another way is that you have the group in the middle, the blues there are called transition elements. Yeah.
So why is it that it's like on the left side it starts from 3 over to 8, but then 8 is 3 of them, and then 1 and 2 are next?
Right. Long time ago, they named the groups. They didn't name these as groups because they vary a lot. They said, well, the groups that behave similarly all the time are 1, 2, 3, 4, 5, 6, 7, 8. Then after a while, they would say, well, that's kind of rigid. These can sort of display the similar characteristics, and then they end up saying, name these the B's. And it's goofy. Okay, so the main thing though is now we have transition elements, name group elements. The main group elements are well behaved. The transition elements are not. Remember I said these are +1 all the time. +2 all the time. -1 all the time, etc. These guys, +1, +2, +4, +5, +6. All those are viable. Iron, +2, +3, very, very common forms of iron. So these are kind of all over the place. That's why they differentiate this group from that. Okay? And we're going to learn why that is also. Okay, here are the 4 groups I wanted you to know. Okay, I'm not so concerned about the patterns, other than it forms a +1 ion. And we'll talk about ions, what that means in a little bit. Later on, I'm going to get into why these properties exist. But for unit 2, alkali metals, alkali earth metals, halogens, noble gases. By the way, there are 2 names for inert gases and noble gases. Noble gases is a really old term, and it had to do with going back to the aristocracy of Europe and all over the world. And the nobles, royal family, they associate with the plebes, the plebeians, commoners. No. They didn't. That's where the name comes from. In other words, they're by themselves, extremely stable. They're also gases, and they're also inert. So they're known as inert gases or noble gases. Our book uses noble gases, but you'll also see inert gases as well. Okay. All right. So just focus on the ions that it's charged. Okay. Now, atoms can lose or gain electrons. Why do you think they lose or gain electrons?
Become stable.
Stability, exactly. Become more stable. Otherwise, why do it, right? Again, stability rules the game. Every unit in this class, I'm going to talk about stability. So when we lose negative charges, for example, oxygen has got 8 protons, 8 electrons, 8 neutrons. Neutral oxygen has got 8 protons, 8 electrons, 8 neutrons. Okay. However, oxygen likes to lose 2 electrons to become more stable. So oxygen is not stable at all by itself, but it's really stable. It loses electrons. Goes from oxygen to oxide. OXID. Much more stable. Lots and lots and lots of things like oxide. Lots of things. Our world has got a lot of oxygen in the atmosphere, and that oxygen tends to form with other elements. Okay, magnesium. Or protons. Okay. So neutral magnesium has 12 protons, 12 electrons, and 12 neutrons. Okay. So magnesium is in the second group over, the alkali earth metals. Remember those form a +2 charge? Let me, let's put the 2 electrons up here instead. So oxygen is going to gain 2 electrons from oxygen -2. Magnesium is going to lose 2 electrons. Again, stability. And magnesium oxide is the way you find magnesium in the water. MgO. We're going to talk about also why there's one oxygen here, one magnesium. When I have 2 mags, 1 oxygen. Talk about why. Okay, and these are called ions. So ions have a misbalance between protons and electrons. When ion has an uneven number of electrons versus protons, not neutral. When there are more electrons than protons, there's a name for that ion. It's called an anion. Well, anions are negative. When more protons are around, that ion is called a cation. Okay, one way to remember that is that T looks like a plus. And the end is negative. What protons, cation, and electrons are different. So there's 3 kinds of situations. We have neutral, that means electrons equal protons. More electrons, we have an ion, anion. More protons, we have cation. Okay, let's go back to oxygen. You'll see this written like this or like this. Same thing. Where the minus is on left or right side, it doesn't matter. Okay, so how many protons does oxygen have? For your periodic table, the upper integer is the number of protons. That's going to be 8. How many electrons? Yeah. 10, because we have 2 extra electrons. We started with 8, add 2 to it, it's 10 electrons. Magnesium. Okay. 12 protons. How many electrons? Yeah, 10, because we have 2 less electrons. Now I have some worksheets for you. I'm going to post practicing this. I have one where it's neutral, and the other one where there are ions. I already mentioned the four groups. We have +1 for group 1, +2 for group 2, -1 for group 7, 0 for group 8. Now, there's another term you've probably heard, isotopes. An isotope has to do with the number of neutrons. So we can have carbon in two different states. Carbon's got protons. Neutral carbon has 6 electrons, and carbon 12 has got 6 neutrons. Carbon 14 has got 6 protons again, because that's what determines carbon from anything else, 6 protons. Neutral carbon has got 6 electrons, but it has 8 neutrons. Now, the way we're going to write these is on the left side of the symbol. We're going to put the number of protons on the bottom. On the top are protons plus neutrons. The carbon 14 has a total of 14. The other way we're going to write this carbon 14, carbon 12. So this is the upper number. This will seem very common. This is a pain to do in a work project. Let's use the equation editor, which is real pain to use. Okay, so the number of protons are equal. The number of neutrons are not equal between an isotope. Carbon 12, carbon 14, same number of protons, same number of electrons, different number of neutrons. Okay. Top number is frequently called mass number or the atomic mass. You see atomic mass used more frequently. Atomic number is the number of protons. Symbol itself and then it's the okay. Now, a lot of people, when they're filling out that worksheet with you guys, look up the base of neon, it's 10, right? We'll say the atomic mass 20.2. 20.18 is an average of all isotopes. This particular one, this specific isotope has 20 protons and neutrons. This one here has 21 protons and neutrons, 22. So the number on the periodic table says 20.18. That's the average of all the isotopes in nature. So there are more 20s than 21 and 22, because the average is closer to 20 than to 21 and 22. So an atomic mass is specific for an isotope. Right? It's not to be in, there's a counting part. You can have a fraction of the part. The reason why this is a decimal because it's not part. And it's a special kind of average called a weighted average. A weighted average has to do with percentage of naturally occurring isotopes. Okay, so we need to go back and forth between these columns. The practice, and that worksheet will give you practice doing that. Now, if we were to go and sample all the hydrogen in the world, 99.985% will be 1,1. 15% is 2,1. Less than that, significantly less than that will be 3. When you look at atomic mass, periodic table, the hydrogen it's 1.01. That's because the one there are more ones than twos and threes. Hence the average. Other ones that don't. So when we're calculating these numbers here, we have to take into account these percentages. What we do is we multiply this number by this number, plus this number by this number, plus this number by this number. That goes all up, we get 1.01. If you look up carbon 12 is mostly almost 99%. We have a little bit of carbon 13 and carbon 8, carbon 14. So the molar mass, the atomic mass of carbon is 12.01. 12.01 and exposure to 12, most of it is 12. And that's called a weighted average. You take into account the percent. That's the weight factor. That's the beginning. So it's not strictly these three up. You've got to pull in the percent. Weighted average. Okay. So the atomic mass, that's that decimal number again. It's, if you take a percentage in nature times the mass, add it all together, that's how you end up with these numbers here. Okay, so this is how you do it. Okay, so we're taking 75%, convert to decimal, times the mass of the one isotope, 34.97, add to that 36.97. At point 2423. What we're doing here. We add those up, we're going to end up with 35.45. Okay, so it's the percent abundance converted to decimal times the isotope mass plus percent abundance times the isotope mass. Add those together. That'll give you your decimal number. Very accurate. And it's just the averages of all the natural curves. Okay, here's some more practice. Okay, that's chapter 4. Okay, I gave you this slide on the top. Now, in Mondo, we're going to post some more worksheets besides the practice problem that should. What there's some worksheets. I'm going to post the answers. Also, problems. I don't know why I can. All right. Here's the wrong. I'm going to post the video also in chapter 3, the last third of chapter 3. Chapter 10. Well, the real wearing shorts right now.
I mean, I grew up in Seven around that's what I wore all the time.
Yeah.
Yeah. I love the dinosaurs there.
Oh, really?
Probably die. Like more money.
I feel bad. Right.
I didn't know you. Yeah, dude. And I was like, where's your last? What is the Kevin Club? Something or other. Other way to make things more fun. Yeah, both Kevin.
No state.
Oh, when the density allowed me to. That's had some question. That's what the density lab was.
So we said it's basically the pre-lab.
That's just Was it?
You guys take care of it.
No, it's,
Oh,
it's the one that we did.
The one
We were
you
actually
passed?
present for.
no,
I submitted it.
on my list.
Okay, oh, you submitted on.
Yeah.
Okay.
He said PDF.
Okay.
Okay, so we have the column.
And then last time.
The column, yeah.
Close. What happens when the host dies?
Ooh, that's a good one. So either one of two options, actually three options. One, the clone dies just immediately. Two, people come down to take care and kill the clone. Or the clone now takes the place of that person.
Missing parts. though. Forget the purpose
Yeah,
of
that's
the
true.
clone.
That's true. Yeah, that's true.
Because the clone's not always completely perfect. It never carries the genes. 100%.
Well,
It's an exact replica of Earth.
Ever.
basically
Yeah,
what
and the idea is their purpose in life was to supply parts for the host. Host gets loses a kidney. Clone, sorry, here you go.
Are you talking about the island? That movie?
No, I'm talking about the slice like novel and art.
Ah,
I'm just bouncing ideas around. So we have a religion. Like as a clone, why do you want to give up stuff? Well, you will attain higher levels of religion. And to justify why the clone is used.
oh, so like in like aggressive form of Scientology.
You know, I did see, you know much about Scientology?
Only that it's only just like the stuff that makes fun of it, like given this much money and you know, oh, the AC is yeah.
Well, they have something in there called an omega. And the omega is this. I was involved in Scientology. It is omega that will help you through your spiritual journey. And if you decide to get out of Scientology, the omega there is to guide you back. So in my religion, in my book, I was thinking of that concept is why would a clone stick with this? Giving up parts and all that stuff for higher spiritual elevation. Yeah. What happens if the clone dies and the host is still alive?
another clone.
What if the clones want to have children?
What is the sole purpose of the correct me if I'm wrong. Sole purpose of the clone is just to supply. So they wouldn't have to in turn like give the clone what regular-
Freedom,
Yeah,
stuff
like
like
what
that.
you would just confine it in
That is-
space. They keep it kind of like a plane.
Kind of like the giver. Remember that movie?
No.
It's basically utopia where only one person knows everything about like the past events and stuff like that. Like they're in a very
Sorta.
sheltered society.
Didn't they make a movie
It's-
about it?
Yeah, they made a movie about it.
The movie's really cool.
Yes,
More
It's like the book
Basically,
is
like-
it's like more.
they take like a drug every day that blocks out color for them
more
and emotions. Like they are basically blank slates that are given a job at like a certain age, and then from there they start like learning how to do their job, and then they eventually take up that profession. The main character of the story got the job giver, or I think it's giver. I think it's
it's
yeah.
called giver, yeah.
Well,
The dog.
Well, it was either that or that was like the job
Well,
of the person giving him the
sorry.
memories.
He's to be the taker, which is the
That's
person that receives all these
Yeah.
emotional stimuli from
So-
the giver and then eventually becomes the next giver. But more concisely, the story is an Orwellian type of dystopia where the progenitor of a society decided that emotion is the root cause of unhappiness. Then they rip out emotion, but they realize that emotionality is required to make certain decisions. So they
have
give
one person.
one person that has that responsibility of all emotion for the entire community. And that person is then given the role of giver, and they have a very prominent voice within the community. But they are also like limited in a way where because they have emotions where everyone else in the community does not, they're somewhat ostracized, not quite ostracized, but because they're like,
I'm pretty sure
they're
they're not allowed to
separated.
marry or anything, or like not allowed to have family or.
yeah, and there's also like a separation of them as a human being because you know, like there's different types of ways you can dehumanize a person, and one of them is putting them on a pedestal. So it's kind of like that, but
Another like,
it has some very complex and great view or like great ideas that are conveyed about emotionality and the importance of it, and how like blind pursuit of a utopia is not quite what we need.
yeah, and then there's like, I know like
That's
from
the-
one thing of it was that none of the families in the community have actual biological kids. They have birth mothers that will basically, they just keep popping out babies, and then they get adopted into other people, like other families and stuff like that. And then I think it's like one of them gets adopted into the main protagonist's family, and it has a defect or something like that. And the community is deciding, okay, we're gonna have to kill off this kid. It has a defect. And now that the protagonist is getting these emotions, he understands, oh, this isn't right. So there's a way to force all the emotions from the taker or giver onto everyone else by that person leaving the community's border. So he takes the kid and runs away and has to like hide from like the authorities and stuff like that. So I think there were people chasing him in the movie.
Yeah,
It was like real close to the end. I think
Yeah.
that's right where they ended it, so they could make a movie.
Yeah,
Um,
but they never did. And I'm
Yeah.
That's like District 9, they're supposed to make a sequel to that.
I heard they're making the second Avatar,
Yeah,
Oh,
I think
yeah,
they
yeah.
are making it. That's gonna be really cool.
and I heard that they confirmed already they're going to make a third.
Oh,
other good narratives
That's-
that you
Like
might
Doom.
consider are
that's
the
kinda
movie The
exciting.
Island,
That
which
means
is
that there's
also
not gonna be as good
clones that are
as-
created for, in their case, rich people. And then they're harvested for organs whenever that person needs an organ.
So this idea I had is not unique.
No?
Well, the thing about ideas is that it doesn't have to be unique, but there needs to be a unique twist
Uh-huh.
to make something
And this
interesting.
movie was called Island.
The Island. The Island.
The Island.
Yeah, and now it's 2022.
Which might provide some inspiration. Another
Did you send
would
me
be,
an email?
oh yeah,
So they're definitely going to take as long as it
and
took to make the
another
first
Yeah.
would be,
They're not-
I haven't seen it yet. I still have to because I have a sci-fi setting that deals
Yeah.
with cloning stuff, but not in the way that you do. It's called Blade Runner. I still have to see it. My friends told me because it's very Mad Max inspired. Setting I'm working on or is sort of Mad Max inspired. Basic principle being, like for example, my idea of a respawn technology is not a unique one because Borderlands has done it. But the thing that I like to put on as a twist in my setting is that before a person dies in this setting on this planet,
I'm going to have to.
Good talking to you guys.
essentially the cloning is imperfect because it uses memories, and memories can be altered, disordered, blah, 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 blah. Which means that a person thinks and remembers that they died a certain way. They can come up with a scar on their new body, which leads to two major things that work in my setting. One is clean and dirty killing, because killing is not seen as much of a big deal. People just revive. But a clean kill would be done quote unquote ethically, quickly, so that the person doesn't suffer and so that they don't have any debilitating effects afterwards. Dirty killing being not immediately.
Torture, sort of.
Yeah. Like for example, to have a person have a likelier chance of losing a limb in the respawn. And then because of the concept of dirty killing also creates an an underground environment of narcotics in order to produce a permanent high. Like for example, if a person is, in my setting, if a person has a mental state for too long before death, it could potentially carry it over. So then drug rings and all these different things. So
Have you seen Gattaca?
I have not.
Oh, cool. It's been around a long time. The kind of cool thing is the title. When I tell biology, my students kind of watch it. Tell me what the title is.
Oh, I also looked at the strontium thing. It turns out that they do strontium analysis in forensics, from what I can tell, and they use strontium isotopic ratios, and I'm guessing they use a half-life for it. Because I know that strontium 90 as an indicator time since death. But I think it's because of the nuclear tests. They can kind of make an educated guess on essentially, in general, when something was created. Like I know for wine, they know if something is a certain vintage by the relative strontium levels within the wine. And I know for
with people,
yeah.
When you breathe in carbon dioxide, breathe out, and all that stuff, once you die, you stop doing that. So then they know the half-life of carbon-14,
Mhm.
and you can then see how much carbon-14 is left in a given sample. And you know the half-life, you can backtrack and find how many half-lives it was, because it's fraction or multiples or whatever. And that concept is they use probably the strontium too, looking at the half-life and stuff. And it's really straightforward. It's not, the carbon-14 is, it's fairly accurate within a range. If you get out of that range, it's not all accurate. And a lot of religious people quote that when it's out of the range. Oh, how can you tell this is that old and all stuff? But within a certain range, it's pretty good. And they have other age testing methods, also radiological days. The concept is half-life. And the reason why elements have a half-life is to become more stable. And this is what everything wants to do. Now, heavy stuff is lighter. Light stuff fuses together to get heavier. And head towards that. So it's nuclear chemistry is really. In certain classes, I teach a unit of it. Like in my nursing class, I just taught a unit. I wanted to make sure they have a little bit of. It's when I gave you the differential equation. For them, I give them the actual. And they, when you have an exponent in the variable in the exponent.
Oh yeah. For like
these logs. That was really good math for that. I mean,
yeah, it's not intuitive until someone explains it to you, and then you have to like remember. Oh, you go in a little circle, and then you have to practice it because it's.
Well, yeah. So x squared is the same as 2 times the log of that. So what I do is I reteach that law. So, but the cool thing is you know, they need a lot of half-life problems. And I used to teach intro chemistry. And there we had did a whole thing on energy, one of the modules. And so one of the energies, nuclear energy, there's alternative energy, there's also all nano chemistry for each one. And when I got into the nuclear part, I did really simple half-life. It was always a multiple. One half-life, two half-lives, three half-lives. So they didn't have to do any logarithms. I did it graphically, you know. You know, oh yeah, chunk, up, three half-lives. It goes down by half each time. In my other classes, it's fractional and stuff.
One question I had from your lecture is the reason that they moved to silicon because it has similar chemical properties to uranium and probably more prevalent, I'm guessing. Like for transistors.
Oh, I don't know why they chose uranium first. They ended up making, I'm an amateur radio operator. I'm not practicing anymore, but it's WB6RD. And in high school, I was really into electronics, big time. And all the stuff I did, this is in the 60s now, vacuum tubes. And solid state stuff was definitely there, but it was still not. Because I got all surplus equipment. I used to work out at Cullen, and if you did work for them, they let you into the warehouse. And this is trying to get out more. I got some time machine. Oh, great. And I did a newsletter. So it was really fun. Anyway, I didn't do too much of that. When I was in graduate school, my thesis was on doing statistical modeling of instruments detector. And so I was starting to take digital electronics. I can understand the detector, how it works. So I stuck to the statistics rather than more of the electronics. But nuclear chem is really fun. Remember I talked about the two protons being super close together, wanting to fly apart. There's an image. It's super strong because of the distances. Really small.
That would be the term known as strong forces, right?
Yeah, and they usually measure it's called binding energy. That's why this has got the most.
And I know this is an odd, curious question, but if there's space between nuclei within atoms, wouldn't that mean that because air is made out of atoms, like gases spaced out, wouldn't that mean that there would be a perfect vacuum between, say, like a brick of, I don't know, like lead or gold or whatever?
Well, read the chapter because there's solid, the common states of matter are solid, liquid, and in the solid they vibrate and they don't move translation. In other words, the nucleus does not move, but all little parts vibrate. Liquids, they vibrate and move. Gases, they do that as well, but they're separated along. So in between this gas molecule, this gas molecule, so that's why there's nothing that's such a big deal of work. Except all the masses in that little tiny area. That means we're walking on nothing. How do you convince someone back in 1900 that that's not solid? That's where Thompson's plum pudding makes more sense. You know, it's solid. Yeah. But it's not.
I wonder if he tried to explain it using lattices, because a lattice you can explain as having a lot of empty space but still be structurally sound.
Yeah, some of those geospheres.
Oh, yeah, yeah.
Same concept.
Oh, I did have one question. The lab 3 density is uploaded, right? As a and lab 4, that's basically just going through like the lab 14 last Thursday. Doing that and uploading it.
Yeah, the lab is percent composition. They either call it lab 4 or lab 2. They can call it lab 4. It's the second wet lab. I think we call worksheets a lab, not a lab. Doing it in the lab time, but it's not a lab. It's so confusing though. That's why I printed out the title as opposed to the lab number. But everyone, it's the next one. And it's a real kind of chemistry lab. The other one.
I was just confused with that.
You know, it's on my phone, I can't see stuff. Try to turn that stuff around fast. You gotta eventually do it anyway, so. When I see the Twitter, I go, oh. Because as a student, I wouldn't want to, same with grading. It doesn't mean it's much. If you get that right away, you know, oh, yeah. All right, good talking to you. Oh, how is this? What? Is this class rolling for you, okay? What is it? Better.
It's nice to have a history lesson because like can't really it's hard to understand why we have different why we have different views that we do without understand what came before. And also because I'm a history guy with that society. One of my favorite sayings was because people say, oh, history repeats itself. One of my favorite sayings is history doesn't repeat itself, but it sure as damn how rhymes. And also because history talks about different economic and social political systems that are that way when people hear these big words like capitalism, socialism, communism, they know what like it actually means in social context and
You know, I don't know English terms. I'm serious. Oh, it's communist. It's a communist.
But it feels like it flows well because I have like at least a decent enough memory with chemistry. But it makes sense to me. I mean, like
I remember some spot too. It's also prepping for one of the what I move on Thursday. This hits the spots. Like a piece of 1A or something. It's really hard. The class moves fast and the summer moves faster. Work for me. With your tenure track, it's spread over 4 months. Anyway, take care.
you too.
Okay.